Hi, colleagues. Today we are going to listen to Aviral. And Aviral Kumar is a final year PhD student at UC Berkeley. His research focuses on developing effective and reliable approaches for sequential decision making. Towards this goal, he focuses on designing reinforcement learning techniques to static datasets and on understanding and applying these methods in practice. Before his PhD, Aviral obtained his BTech in computer science from IIT Bombay in India. He is a recipient of the C.V.N. Dolat Ramamurthy Distinguished Research Award given to one PhD student in EECS at Berkeley for outstanding contributions to a new area of research in computer science, Facebook PhD Fellowship in Machine Learning, and Apple Scholars in AI ML PhD Fellowship. So, please, Aviral, please start.
Yeah, thank you so much for inviting me in for the introduction, and my apologies for this whole technical glitch. But today, I guess I hope I'll still be able to finish in time because my talk is not that long. So today I'll talk to you about sort of RL from static datasets, and we'll talk about algorithms, analysis, and applications. I don't have to cover everything in this talk. It's a very high-level overview talk, so please feel free to ask any questions in the middle, and even if that takes a long time, I'm happy to go over them. Okay, so there's actually been a lot of progress in machine learning out there, right? And this talk, the slides are from 2 months ago, and I'm pretty sure that whatever I'm going to show you on this slide is already backdated, and so the rapid pace of progress is quite rapid. So back then, at least 2 months ago, there was it was still the beginning where ChatGPT was just out, and we saw we saw the power of generative models in generating images or natural language. And we've also seen a lot of progress in prediction problems, such as neural networks predicting structures for very, very complex objects, such as proteins. Now, while all of this, and including the progress that has been made in the last 1 or 2 months, this is all quite exciting, but there's still a little bit of a problem. And the problem stems from the fact that most of these methods that we utilize in trying to solve these in these advances that I showed to you before, they rely on supervised or unsupervised learning. What do supervised and unsupervised learning methods do? They end up taking a data set and fit a model to the distribution over inputs in this data set. So it could be a generative model over images or language. It could also be a classifier, which is predicting labels, the distribution over labels given an image or something else. Now, this is quite good if you just have a lot of data and you want to train some model on it. But this paradigm of modeling the data distribution alone is not quite enough in many problems out there. And to understand what I mean by this, let's look at a concrete example. So let's say I gave you a data set of some chip designs. And these data points in this data set are annotated with the runtime it takes to run some kind of a workload on this chip. So it's a number that tells you how much time it would take if you were to run something on this chip. Now, clearly, some of these chips are pretty good. For example, something that takes only 5, let's say, milliseconds, whereas some others are very bad. In this problem, a very sort of practical goal where machine learning is being utilized out there today is to discover a new chip that is better than the data set in terms of this runtime method. So given this data set, my goal is to come up with an ML method that can find me a new and a better chip design. So let's imagine what would happen if I were to apply supervised or unsupervised learning to this problem. What I can do is I can fit a model that can predict runtime of a new chip by doing supervised learning, or I can model a distribution over chips in this data set via unsupervised learning and sample a new chip from that distribution. But turns out neither of these actually allow me to make progress towards this goal, because neither of these models allow me to discover an object, in this case a chip, that is better than the data set, that attains a much smaller runtime value than any chip in this data set. All they do is they model relationships between variables in this data set, and that's it. They don't go beyond the data or are not better than the data. And that's kind of the key requirement in this particular problem setting that I described. So turns out that a very similar goal of sort of discovering in an abstract sense decisions that are better than any decision that you have executed in the past appears in many other problem domains as well. So this includes problems in robotics, which I think you all probably are very familiar with, where we want to be able to come up with policies that are much, much more successful at solving a task than anything I could hard code on that robot. Likewise, in healthcare, where we want to be able to find treatment plans that lead to much better recovery rates than any treatment plan that a doctor would have executed before. And finally, also in sort of more scientific discovery problems where we want to be able to discover materials, molecules, objects, etc., that attain some favorable properties, like the lowest energy material structure, for instance. In all these problems, I want to be able to go beyond the data and discover a new decision that is better on these metrics that I described to you here. But just standard modeling of the data alone is not going to be sufficient to do that. So what my research tries to do, or what I'm going to talk to you today about, is sort of trying to solve this problem of discovering better decisions in one particular paradigm. So one way to formalize this abstract goal of discovering better decisions is to formulate this as the problem of optimizing decisions to maximize some kind of a utility or a reward function. So what do I mean by this? I mean that if you can specify how good a particular object or a decision was in terms of a scalar number, you can simply optimize that number with respect to the decision variables. Now, once you pose this problem in this manner, there's actually already a number of subfields of machine learning that try to solve such problems, which includes reinforcement learning, that is the primary topic in this talk, also bandits, Bayesian optimization, and many other fields as well. And typically, the way these fields all approach this reward or utility maximization problem is by doing some kind of trial and error interaction. So a classical example of this is the game of Go, where essentially a reinforcement learning technique was left to interact with the simulator of the game of Go. It played this game over millions of times, initially failed at it, but then observed the feedback that it failed and used that feedback to now improve over time. So clearly, like, iterated learning via trial and error is sort of the key paradigm that has been utilized to solve this problem of optimizing decisions. But turns out that if you think about this paradigm in the context of real world problems, there's a big issue with this paradigm. And the issue comes from the fact that this sort of a paradigm of improvement by trial and error, by interacting with some sort of a simulator in this case, is quite problematic when we think of applying these methods in the real world. So what do I mean by this? I mean that interaction in the real world often inhibits the ability of these methods to collect lots and lots of data where in the real world problems. And to explain that a bit more carefully, let's look at some real world problems where interaction is quite expensive. So one of them is drug discovery, where collecting just one unit of data point would take about 1 to 2 months of work to collect. So it's quite expensive to simply even run an experiment or run an action in the real world. Likewise, in robotic problems, oftentimes interaction poses a lot of safety concerns, and this is probably something much more relevant to you guys, where you need a lot of careful instrumentation to be able to collect lots of data, and you will end up facing problems such as a breakdown of the system on the hardware side. So because of these reasons, data is not quite easy to collect in a scalable manner if we simply rely on interaction, which these prior methods do. And why am I making such a big deal of data? That's because data at this point is sort of the central ingredient that powers machine learning methods. So if I look at some plots from or some analysis of large language models that is still already backdated, but this is a plot from some state-of-the-art models about three months ago, you can clearly see that sort of the key ingredient that often enables you to succeed is taking a larger or more diverse data set and maybe even training a smaller model on that data. So clearly, data is a very crucial ingredient, but with these methods for decision making or for optimizing decisions, we can't quite collect this much data because interaction is not a scalable way to do so. So what can we do to solve this problem? So what my research has done so far is to develop methods for optimizing decisions that can incorporate existing static, previously collected data sets. So the idea is if you can collect some existing source of interaction data from the real world, and this could come up by just logging all data of interaction that we have, like logging all data from self-driving cars or logging all treatments that were prescribed to patients, we can now simply learn to optimize the decision using just this existing source of interaction data. So in some ways, this paradigm does not make any active or online trial and error queries in the real world. So it's an offline learning paradigm. And we can solve this question of maximizing reward in many ways. And the way I have considered in my work is to solve this using reinforcement learning, the paradigm and the formalism of reinforcement learning. And so what I'll call this paradigm of optimizing decisions or maximizing reward from static data, I'll call this as offline reinforcement learning. And I'll talk to you today about a variety of aspects of offline RL. So the first part, I'll talk about some challenges that come up when we think about trying to do offline RL. When we try to when we think about learning from trying to improve over a given data set. And I'll then discuss some algorithms that I've developed to address these challenges. I'll then talk about some real-world applications of these ideas that I've worked on in domains such as chip design, in robotics, as well as some more recent work in chemistry. And finally, I'll talk to you about what can we do to scale these methods up. So how can we make them also utilize or also benefit from large models? That's the other sort of ingredient that modern deep learning is benefiting a lot from. So let's get started. And I'll talk about challenges and algorithms first. So before I dive down into this, let me set up some quick terminology. So the biggest object of interest here is this existing source of interaction data. So we'll assume that this existing data consists of tuples of 4 elements. And to understand what each of these look like, let's ground this in an example where each of these elements are coming from data collected by human drivers driving a car on a particular road. So we'll use xi to denote the observation or the state of the world at a given point in time visible to the data collection strategy. So in this case, it could be the position, the velocity of the car, and the position, etc., of other vehicles around it. In this case, there's no other vehicle, but you can include all that information into sort of a vector that is the observation. We'll use action to denote the action that was. We'll use AI to denote the action that was taken by the data collection strategy at this particular point in time in the world. So in this case, the car moves forward, and hence AI is the action that takes the car to the car ahead. We'll use R of xi AI to denote a scalar reward value that in some intuitive sense is an indicator of how good this particular action was. So was it an action that led to a crash? Clearly no. So it's an okay action, and we'll give it a reward of +1. And we'll use xi +1 to denote the subsequent state of the world when the action AI is executed. So it's the sort of the next observation. So next state of the world after executing this particular control. So given this data set of xi AI, R of xi AI, and xi +1, our goal here is to find a policy, which is nothing but a mapping from observations to action. So you're producing the best possible action for a given observation, such that if you now use this policy to make a sequence of decisions or a sequence of actions upon deployment, the total sum of rewards that you get as a result should be maximized. So this is sort of the most general formalism of trying to make a sequence of decisions and maximizing the rewards you will get for each of them. Now, this is the most general setting, but for some visualizations today, I'll consider a simpler setting where we'll put t to be equal to 1, and we'll call this one-step offline RL, which is we'll only consider a setting where you're making one decision so that you can maximize the reward that you get, and that's it. But all of the methods that I'll talk about today are more generally applicable. This is just for ease of explanation and ease of visualization of the key ideas. Okay, so let's start with why is offline RL hard? So this is challenges in offline RL. And to do so, I'll start with a little bit of an intuition. So the intuition for why offline RL is hard is because counterfactual estimation tends to be hard. So what do I mean by this? Let's say I have this human driving data set that I described to you earlier. And now my goal now is to learn a policy or learn a way to control this car that can maximize the comfort of any rider sitting in this car. So to do so clearly, what I would have to do is at an abstract level, think about what possible actions could be better. So I'll have to evaluate a set of candidate actions that I could have executed on the car at this particular point in time that would enable me to maximize the comfort of the rider. Now, some of these actions are pretty good, while others are pretty bad. For example, an action that throws the car off the road. And these are all possible candidate actions I would have to consider while trying to find a better action. But now the question that comes up is, since this set of candidate actions consists of both good and bad actions, how can I correctly estimate how good each action is, or correctly estimate the outcomes of each of these unseen actions that I'm considering? And more importantly, how can I make sure that I can precisely filter off the bad actions? None of these actions have been seen in my data set, and I want to do better than my data and find something new. But clearly, I need to be able to know what things are not good and I need to avoid. And so precisely this issue with estimating the outcomes or estimating the goodness of counterfactual actions is the key problem that comes up, or the key challenge that needs to be addressed in offline RL. We need to be able to evaluate reliably how bad these particular actions are. So this is a very intuitive example at a very high level, but let's try to sort of ground this into a concrete visualization that we can also then use to understand some methods that we can develop to start to tackle this issue. And to do so, as I mentioned earlier, I'll consider the one-step setting. So one step of offline RL where you have an observation xi, an action AI, and an associated reward value R of xi AI. My goal is find an action for a given x that maximizes the reward you will get. So simply one action to maximize reward. That's all the goal. For visualization, I'm going to consider a simpler setting where I'm assuming that the action AI is actually nothing but a 1D scalar value that I'm going to plot on the x-axis. And I'll visualize the reward function, the ground truth reward function for all actions at a given value of x, which is given value of observation, on the y-axis. So I'm just drawing a little toy plot that shows the ground truth R of xa function as a function of a on the x-axis. Now, I remember that I only have access to a static data set. That's the setting of offline RL. And so I'm going to mark the data set as these green colored crosses, which correspond to a particular value of action and a particular value of reward observed at that action. So these are the data points in my data set. And my goal again here is to find a distribution over actions or a policy that attains the highest possible reward. So that coincides with the peak in this reward function shown in blue on this plot. Okay, so this is sort of the problem setting, but to understand why this setting ends to be challenging, let's try to look at a very simple like first tab recipe you could choose to do if you want to solve offline RL. So that first tab recipe looks like the following. What you can do is you can take this data set that you had with you, and you can apply two steps. First, you can try to take this data set and distill the reward values in this data set into a model of the reward function. So note that you only had access to samples of actions and the associated reward values. What you can do now is you can try to fit a parametric neural network model R of xa, R theta of xa, that can approximate the reward values for all possible actions. Once you have this model now, you can in principle query this model for any possible action and any possible observation. And hence what we can do is we can now say, well, rather than trying to find a policy that maximizes ground truth reward, which we do not have access to beyond just these samples that I'm seeing in my data set, what I can do instead is I can try to find the policy that maximizes the learned reward model's predictions. So the reward model that I obtained in step one. So very simple recipe, take a data set, convert it to a function, reward function, and maximize that function. So to understand why offline RL is hard, let's look at what will this recipe do in a more careful way. So starting with step one, where we are trying to learn the reward model. So I'll bring back our visualization from before, and we'll make a sequence of logical statements. The first is if I were to fit a reward model on this data set using, let's say, supervised learning, I'll very likely be able to make sure that this learned reward model's predictions closely approximate the ground truth reward function R of xa in expectation under your data set, because you're doing supervised learning, and supervised learning can work pretty well. However, there's no guarantee that this reward model is going to make good predictions outside the data or on unseen actions in particular. And the reward model's predictions in red in this case can be arbitrarily different from the ground truth reward function. So with this reward model that you learned in step one, we can choose to now, and also this is sort of in a more technical sense, this is an artifact of distributional shift, where models trained via machine learning methods are not generally robust to changes in distributions over the input variable, in this case, the action. So with this sort of incorrect reward model, we can ask, how does it affect policy optimization? So how does it affect learning of the policy? And to do so, I can visualize this by initializing the policy somewhere in the space and trying to solve for the action distribution that maximizes reward model's predictions, in which case I'll find this particular peak, which you can see here on the slide. And once I have this policy now, I'll deploy this policy out there in the environment, and I'll instantaneously notice that my policy accrues a much, much lower reward than what I thought it would get. So while my policy attains a really bad reward, which is much, much worse than any reward I would have gotten if I were to simply choose a random action from my data set, my reward model is thinking it's going to get a really, really high reward. So clearly, the policy did not solve this task. So what happened? What went wrong? You can summarize what went wrong in the form of the following flowchart. In step one, the reward model ended up being incorrect on unseen actions, and this was because this reward model was not never trained on counterfactuals that it had not seen. And then these errors, especially the optimistic errors in the reward modeling process in step one, got exploited by the policy optimizer in step two, and the policy ended up finding actions that it thought would lead to a really high reward, but in reality did not. And that's precisely the challenge that comes up when you cannot estimate the outcomes of counterfactuals reliably. So you can think of one of these peaks as basically an action that throws the car off the road, and the policy ended up thinking that that action will lead to a really high reward, and that is precisely because the reward model made incorrect predictions on that action. I heard a sound of a question pop up. Is there a question by any chance?
Yeah, I asked a question. So
Yeah.
this seems to be similar to the RLHF stuff that was used in ChatGPT. So
yeah.
This means like ChatGPT might also have the same issue, and maybe the key is to make sure your data set for the reward model is, I don't know, cover as much distribution as possible.
So that's a great question. So yes, I mean, in fact, like the reason why RLHF used this chart, in fact, the method I'm going to talk about today from like 3 years ago, or actually maybe even 4 years ago, is kind of what RLHF uses. So RLHF is not like sort of a, I mean, in some ways, like it's exactly a very similar problem, and that's what they use it. I think the point about collecting data in the right way, you're absolutely right. If you can collect data on actions that or on sequences in the RLHF case that you have not seen, you should collect it so that you can learn an accurate reward model. I guess it's not true in general, right? For example, imagine if you're doing driving, or imagine you're doing, imagine in the case of robotics, right? Like a lot of these actions would amount to some control signal that would make the robot hit into a wall, let's say a navigation robot. But you really don't want to do that because it's going to destroy the robot, destroy the surroundings. So in some ways, you will inevitably not be able to make the reward model correct on some actions. And so there's only two ways now. Either you know those actions and you can account for them in some way, or you somehow utilize the fact that your learning algorithm accounts for sort of bad behavior. So in some ways, like sometimes like you cannot verify these actions. You cannot collect data on these actions, but in RLHF you can. Yeah.
I see. Thanks. But I think like the thing you mentioned, I mean, it can potentially collect data from simulation, but I mean, yeah, it also has its own issue that other agents' reaction might be hard to model.
Yeah, and also sort of the obvious point about like gap between simulation and real world as well will come in, right? That's also the other thing.
Okay, thanks.
Yeah. Okay, yeah. So I'll continue going on. Yeah, and this challenge is actually a very real challenge. So we've applied this in we have seen this kind of a thing come up in robotic manipulation. We have seen this kind of a thing come up in chip design. In both of these cases, you actually do find that it's a bit of a problem if these unseen actions or unseen decisions do have really erroneously high values, and those things tend to hurt the policy optimization process. Okay, so what can we do to fix this? There's been actually a long line of work in the offline RL community, both from us as well as from people outside, trying to address this sort of exploitation challenge. And today I'll talk to you about one of these methods, which is called conservative Q-learning from me, which appeared at Nuro in 2020. And before I dive down into what my method does, let's kind of quickly have a look at what prior approaches did to solve this problem. And to sort of keep this discussion grounded, let's consider this two-phase recipe of fitting the reward model and training the policy to maximize the reward model. So back in 2020, when we were doing this work, prior methods that existed at the time mostly tried to solve this exploitation issue at the point of step 2 by training the policy to not deviate too far away from the data. So the idea is that if you can constrain the policy to lie within your data set or close to your data set actions, then in no way the reward model will end up being exploited, because the reward model, if it was trained properly, would end up approximating the ground truth reward values very closely on these data points. But this approach tends to be quite restrictive because it does not allow you to sort of go beyond your data or rely on generalization properties of your reward function, which are not always going to be terrible, because your reward function is a neural network that you trained with some inductive biases on some kind of data, and it will generalize somewhat. So this approach of constraining the policy in a brute force manner tends to be quite restrictive. And so sort of the motivating question for us that we had in this line of work was, can we somehow change step 1, where we are fitting the reward model in a way that allows us to sort of leverage the benefits of generalization of the reward function, but avoids this exploitation issue that we just saw in the previous example. And to answer this question, sort of the next natural logical question that comes up is to try to understand why or when does reward modeling or errors in reward modeling not hurt for the case of offline RL. So to answer this question, I'm going to bring back our visualization from before, where the ground truth reward was in blue and the reward model was in this red colored curve. And we do a little thought experiment. If instead of this reward model that you see up here, if my reward model looked like the following, meaning it always attained sort of small values outside the data, then if I were to run policy optimization, my policy will clearly find an action that maximizes not just the reward model, but also the ground truth rewards predictions shown in blue in this slide. So the key idea here is that if we can somehow ensure that the learned reward model's predictions are really not high, or more precisely, they always underestimate the ground truth rewards predictions on unseen actions, then policy optimization is never going to choose an unseen action unless it really thinks that that unseen action will attain a high reward value, which is going to also reflect in the ground truth reward function of that unseen action. So what we did in this line of work was to develop a method that can learn such a model which satisfies this underestimation or this conservatism property, where the reward model's predictions are smaller than the ground truth reward on unseen actions. And the key challenge that comes up here is that you don't really know what the ground truth reward should look like for unseen actions. So how can you actually devise a method that can sort of with high probability give you a guarantee that that looks like this underestimation property is a challenge. And that's what we try to do in this line of work. So what does our method look like? So I'm going to first visualize this idea on this picture, on this illustration, and then we look at the concrete objective that works towards that. So what we can do is we can start off with a reward model that fits the ground truth reward values on your data set. And then what we can do is we can try to take a simple procedure. We can try to find one of these erroneous peaks in this reward model. So find an unseen action that maximizes the outputs of this learned reward model. And then what we can do is we can simply push this peak down. So we can regularize r theta to not have a high value on this peak that we found earlier. We can repeat this process again. So we can find this time the peak is on the other side and push its value down. At the end, if the process converges, we'll be left with a reward model that is conservative, that attains small values outside the data, and for which policy optimization now works. So the step 2 of the problem now basically finds the right action in this picture. So we'll call this procedure conservative offline RL. And the way it works is to have 2 objectives. The first one is to fit the reward model on the data, but then also try to actively seek for high-valued unseen actions and push their value down. So for a more formal treatment, you can write this objective as a Minimax, or you can write this you can describe this procedure as a Minimax optimization problem, where you're trying to find a reward model r theta that fits the reward values on your data set. But at the same time, you're trying to find these unseen actions, these high-value unseen actions using this inner maximization. And you're trying to regularize the model to not have a high value. So note that like you're trying to find mu that maximizes the expected predictions of the reward model under its own self. And then you are minimizing this term with respect to theta, which is the parameters of the reward model. For those of you who are familiar with adversarial training in machine learning, this is a lot like adversarial training, where you're trying to find these adversarial examples and trying to regularize them to not have this adversarial property. So it's a lot like that, but now it's being done on the reward model's prediction. So it's not exactly the same, but it's similar in spirit. Yes, there's a question.
Yeah, thanks. But it seems like intuitively this method, it will just not choose any actions outside of your data distribution. Is it true, or like maybe it depends on the hyperparameter like alpha here?
Yeah, that's a great question. So okay, yeah. So I think it depends on a couple of factors. So the first is alpha, obviously, as you said. I mean, if your alpha is 0, then this should approach like just the standard thing. And if alpha is really, really high, then yes, of course, it shouldn't choose anything beyond your data. But that's sort of not enough for this method. So the main part of this method is the fact that it really depends on the kind of model you're using to model the reward function. So your theta here, r theta, is not just any it's not any arbitrary model out there. It's actually a model from a particular neural network or particular family, right? Particular function class is what it's called more formally. And so if the function class has some, let's say, property that is good, for example, if you know that your 2 different dimensions of your action affect the reward value, ground truth reward value, independently, and you bake this into the architecture. For example, you process 2 different dimensions independently and then sum them up at the end. If you do that, then in principle, you will end up getting a function class that cannot arbitrarily push down values of the reward function on any action. It will always push down reward values only independently over different dimensions. So in some ways, by construction or by construction of the function class for the reward function that you're choosing, you're ensuring that you cannot find a solution that will only constrain you to literally the actions in your data set. It can account for the invariances or the inductive bias or the structure of the reward function that you have in your class. If you literally have a table as a reward function, like literally a matrix of entries over X and A, then yes, I agree with you that it should be nothing different than just staying within your data set. But if not, then it accounts for the structure, the generalization of your function class, in this case, the neural network of the reward model. Does that answer your question?
I see, thanks. I think like maybe you will also introduce some method. It feels to me like you can also maybe having a covariance or like variance from the reward model, and then you can just minus the variance. Is that also some method?
Yeah, that's a great question. So I don't have that in my talk. I have spent quite a bit of time in my PhD trying to do that. I have some thoughts about that. So actually, it's a very it's somewhat of a chancy thing whether that works, at least in my experience. So in the sense that oftentimes when you train a reward model, so the problem is like oftentimes if you compute the variance or the standard deviation of an ensemble of models and use that in some way, it also tends to get exploited. So you can easily find an action for which the variance is small, but that action is still far away from your data. And the reason that I think is because oftentimes when we train an ensemble of models, they don't tend to be diverse enough. They tend to like sort of extrapolate in very similar ways because neural networks learn simplest possible functions. And so oftentimes you can find an action that will also exploit that uncertainty metric of like the standard deviation or the variance. So in my research, I've not found that method to be highly reliable. It often works very well in low dimensional problems, but as soon as you scale up your dimensionality of the action, it tends to sort of break down. And the only thing that works is sort of this more explicit way of like pushing down unseen actions, which this kind of a thing is doing. But yeah, that is definitely a valid approach. And if we get better uncertainty estimates or reliable uncertainty estimates, I think that's a very powerful approach as well.
I see. Thanks.
I think we have also the question in the chat.
Yeah.
The question is, what if the unseen ground truth reward is actually higher? Would conservative offline Q-learning work in this case?
Yeah, that's a good question. So I guess there's 2 points here, right? So the first one is certainly like if you I'll just go to the picture, right? So certainly if like if let's say if in this plot the blue curve was like high up here, this model would end up pushing down this peak. But there are 2 questions that come up. So the first thing is like if you don't know whether there could be a good action outside the data, then how do you even like have the confidence of letting the policy choose those actions? That's kind of the first question. So in some ways, like yes, the method would not work in the sense that it will not find that high reward value action outside. But in some ways, like unless we have some domain knowledge of such an action existing, we can't be confident that that's the right thing to do. The second thing is oftentimes like just offline training alone will not give you the best possible solution. But what you can do is you can do a lot of offline training on lots of diverse data, and then do a little bit of like active data collection where you can like roll out 1 or 2 solutions, 1 or 2 policies out there, collect some more new data and use that. So that's called the online fine-tuning setting. And in that setting, I'm pretty confident that you'll be able to like quickly understand that this action, like this reward here, could be really high, and you will collect data from somewhere here, and then you will find this action outside. So I think, yes, just this method as I'm describing will not work because because it's agnostic to the knowledge of anything existing outside. But if you can incorporate either the domain knowledge or do online fine-tuning, it would start working. So in the case of like RLHF, this amounts to actually deploying the model again and then collecting a lot more human preference data again and updating the reward model. So that sort of thing. Yeah. Any other questions? Okay, so I think I'll probably skip the theory. So you can actually show some theoretical results of the soundness of this approach, but I'll skip that for now. But just one small remark here. So, so far I was talking about the reward model, but then you can also do a very similar thing for cumulative rewards. So what you can do is you can, instead of, if your goal is not just to optimize the reward model's predictions, but rather to optimize a cumulative sum of rewards under your learned policy when you are making a sequence of decisions. What you can do is you can do the same approach, but you can apply it on what is called a Q function or a value function. So a value function in reinforcement learning models the cumulative sum of rewards you will get from a given state and action pair. And so, when you train such a Q function, you get similar kinds of exploitation issues. They tend to only be much more severe, but nonetheless, what you can do is you can use the same recipe of fitting the Q function on your data using any method that you like and pushing down high-value unseen actions like I described to you earlier. And this is what we call conservative Q learning because it's learning conservative Q functions in our paper. Okay, so I had some empirical results on some sort of standardized benchmark domains that I'll probably, maybe, let me just check the time. I guess I'll probably skip in the interest of time, but the high-level TLDR is that actually, compared to other approaches, back in 2020, at the time when we were doing this work, of doing offline RL, which included just doing imitation learning or doing things where things with like these methods that would constrain the policy to be close to the data. Our approach ended up outperforming all of them. And since then, sort of, there's also been a lot more works that use this kind of key principle of like learning conservative models for offline RL, and that has been very successful. So our method, so clearly our approach from our 2020 paper was not sort of the most optimal approach in the sense of implementations. But there's many more new methods, including some of work by some collaborators here, as well as other people in the community, which actually takes the idea and then implements it with the right design decisions that works really well. Okay, so one other thing I wanted to talk about was a little bit of an intuition for why offline RL would do better than imitation learning. So this is a question that I get asked a lot, actually, as to why offline RL improves over a given data set and why not simply do imitation learning or supervised learning on this data. And so the intuition is that if you are doing offline RL, you can hope to be able to do dynamic programming or stitching, where what you can do is you can, even if you have suboptimal sequences of actions or suboptimal trajectories in your data set, you can hope to combine or compose the best pieces of these trajectories to find an overall better trajectory. So what do I mean by this? Let's say I have a navigation problem where I have two trajectories or two sequences in my data set. One that goes from A to D via B, and another one that navigates from D to C via B. And let's say that my goal here is to find the shortest possible path to go from A to C. So I want to find the path that goes from A to B and then B to C. If I were to simply do imitation learning, or if I were to simply sort of clone the actions in my data set or supervised learn, half the times I'll get the action at B wrong, because half the times in my data, I'll see that the action distribution at B is to go towards C, and half the times it's to go towards D. However, if I were to do offline RL, and that is, by that I basically mean we train a Q function, it'll be able to sort of stitch together these subpaths of A to B and B to C to find this path from A to C reliably 100% of the time. And now this is a very toy example, but imagine for a second if you had maybe 10 or 20 of these intersection points or these junction points like B that I'm showing up here. In that case, the probability that imitation finds the right answer or the right trajectory is going to decrease exponentially, but with offline RL, that will not be the case. So this exact problem of compositionality is basically why offline RL methods can improve over your data. So if your data has coverage and it overlaps, you can hope to combine the best individual pieces to find an overall better whole. Okay, so yeah, so that's sort of the main takeaways of this first part, which is the fact that the key challenge in offline RL comes from the fact that we end up exploiting the overestimation errors for unseen actions in your reward model or in your in the model of your Q function. And one simple algorithmic paradigm is to fix this using this conservative methods that I talked to you about. And at least empirically, what we've been noticing and what other people in the community have also noticed is that these methods tend to improve over your data because of the stitching property that I just described to you on the previous slide. Okay, any questions here? Okay, great. So yeah, I think I have to I'll have to like go through some parts quickly, but let me kind of give you a sense of some real world applications. So in a lot of my work is mostly sort of more on the machine learning side, but I sort of got into kind of thinking about sort of real world problems across a number of domains, just to be able to see what like how can sort of the work we are doing impact the real world, and how can we learn from the real world and bring those insights back, bring those problem statements back to our algorithmic machine learning research. And to that end, I've been working on a couple of application areas, or I've worked on a couple of application areas that I'll give you a rough overview of. And then I'm happy to also discuss more after the talk about what we've done in each of these areas in detail. So the first has been this sort of in this domain of hardware, where our goal was to do accelerator design. So our goal was to synthesize a hardware chip that could run certain kinds of workloads really, really quickly. So if I have a certain kind of ML model I want to run on a particular chip, how can I run that really quickly was sort of the question that we wanted to answer here. The second one is this domain of real robots. So here our goal has been to sort of take a giant robot data set, and this is for sort of robotic manipulation tasks, and use it to learn a pre-trained policy initialization, or like almost like a foundation model, a policy foundation model, for kickstarting the learning of new tasks on this robot. And finally, something much more recent and much more exploratory and still under submission is this domain in this domain of computational chemistry, where we've been looking at sort of this problem of optimizing crystal structures. So you have a database of certain crystals and the associated energies that it needs to decompose them. The goal now is to discover the lowest energy stable structure, which is not generally observed, because that kind of a lowest energy structure would be most stable to use in solid state batteries for manufacturing a lot of products. And so it's been a lot of domains out here. And the key property that all of these domains share is that in all of them, actually building accurate simulators is, or accurate and usable simulators is quite hard. So for example, in the accelerator design problem and the crystal structure optimization problem, building simulators, you can build simulators, and there are simulators, but it takes forever to sort of simulate things. So for example, in the chip design case, it would take about 10 days to be able to simulate to find a particular good chip design. Whereas with our method that ran some sort of offline RL, we were able to get a good design in 2 or 3 hours. And the 2 or 3 hours were just spent in running, in this case, the TensorFlow code that we were running, which I'm pretty sure could be optimized much more. Likewise, in the crystal structure case as well, where simulation is going to take about 1 to 2 days for simply one chemical formula. In real robots, simulation is doable, and there are simulators out there, but we have, at least in our lab, we have found it very hard to use simulation and transfer policies directly from simulation without doing anything clever about addressing the sim to real gap. And likewise, on the other side, in all these problems, we have a lot of data that already exists, like data sets that were collected by other people, and we can hope to utilize them directly to now learn to make good decisions, which is precisely why offline RL type methods are a very good fit in these problem domains. Okay, so I had more details about this accelerator design application. I'm going to skip that in the interest of time, but I'm happy to also discuss more later on about sort of what we did and what exactly I'm even still now working on, and along progressing these real world applications. Happy to talk more as well about that. But I want to quickly give you a little bit of more insight into sort of the third part, which is how can we scale up these methods to use large models. And for this, I was hoping to talk about 2 of my papers. I'll talk about some of them. There's some theoretical components here, which I'm going to skip, but I'll talk about sort of the broad results that we've been doing. So the first thing is, why do we care about large models, right? That's the first question that comes up. And the rationale is that large models are the second biggest factor that have propelled modern machine learning. So in the beginning of my talk, I used this plot to show how important data is in machine learning and like large language models, for example. But for a given size of the data set, it seems like larger models or more expressive architectures are much better. And they have emergent properties that actually lead to a significantly better performance than a model of a smaller capacity. So with offline RL methods, in principle, that give us a way to leverage data sets in RL and decision making. But the natural next question to ask is, what about large models? Like, would offline RL methods also benefit from large models in the same way as these large language models or other models in supervised learning? So to answer that question, I'm going to talk about a little stress test or a little experiment that we did where we wanted to train a single policy to play multiple Atari video games together. So now Atari games, if you are familiar with reinforcement learning, is a very common benchmark for RL algorithms. But people typically train on each of these games individually, and we have almost perfected that kind of training. We have got methods that can train really fast, really well, and perform and give us really good policies individually in each of these games. But now we took one step further and we said, okay, what if we wanted to learn a single policy to play all your video games together? What would it look like for offline RL? This is a little bit of a challenging problem because a lot of the times different games exhibit conflicting optimal behavior. So we want to learn to operate differently in different games because the dynamics of games are very different to each other. And yet we want to be able to train one single model to play all of these games together. And to add on to that, we had about 2 billion data points in our data set that we were training with in this case. And the data was highly suboptimal. But we still wanted to be able to figure out much more optimal game playing behavior in this case. So simply imitation learning will not be the best solution is what this tells us. So if in this problem, we look at scalability of different approaches, as in how much performance difference happens when you increase model size. Turns out that for imitation learning style methods, you get a considerable performance increase if you go from a smaller transformer to a larger transformer. But with offline RL methods, this gain tends to be quite modest, quite small. And turns out if you scale up model capacity quite a lot, performance even starts to decrease with very large models. So clearly, there's something off with between supervised learning and offline RL. And we wanted to sort of understand what is going on here. So what we did in this line of work was to think about this question of why it is hard to use large models in offline RL as the question of trying to understand why it is easy to use large models in supervised learning, and then bridging the delta between offline RL and supervised learning. So the difference between offline RL and supervised learning is the kind of objectives that we use to train with RL versus supervised learning on a given data set. Now, there's actually a lot of interesting understanding work on trying to understand why large models work well in supervised learning. And I'm going to tell you very briefly what it is like. So one of the arguments that exists out there is this argument of implicit regularization. So the idea is that if you take a very, very big model and you minimize a supervised loss L theta over this model, turns out that you will end up finding solutions, if you do this by gradient descent, that also end up being regularized in some way. So you end up, in effect, minimizing not just the loss function, but also some kind of a regularizer added to this loss function. So, and the hypothesis is that this regularizer sort of prefers good solutions. It prefers solutions that are simpler or regularized in a way that it does not overfit and it performs well. So with this in mind, what we tried to do in this line of work was to have this hypothesis, which is implicit regularization prefers simple solutions in supervised learning, and backtrack our way to understand what this thing looks like for the case of offline RL. If the hope here is that if we can understand what this implicit regularizer looks like for offline RL, we can use our way, you can use it to figure out why offline RL is broken with large models and how do we fix it. Now, I'm going to skip a lot of theoretical results here, which is not that relevant. But what we found was when we derived the implicit regularizer, there was one term in this regularizer that only came up in the case of RL and was problematic in terms of using model capacity, using large models. So what we did was we simply undid that term. We simply added that term back as an explicit regularizer to the learning algorithm. And just by doing that, we found that we were able to develop an offline RL method that benefited from performance improvement of the same scale as supervised learning. So now when we go from a smaller model to a larger model, offline RL methods, in this case, yellow. In this case, the offline RL method is CQL, and we are adding a tiny bit of regularization on top of it. That ends up performing really, really good when you go up to a larger model size. Pretty much how supervised learning benefits from model capacity. And not just this, but actually turns out that if you take this and you look at absolute scores of different methods, you find that while prior methods based on decision transformers as well as imitation learning are not so good, which is expected because this data is highly suboptimal, our approach, which is taking conservative Q learning from before and adding this implicit regularizer, this regularizer that I talked about, that I did not go into the details of, but happy to after this. That regularizer, if we add on top of conservative Q learning and use a large model, we are now able to improve a lot more beyond the best prior number on this benchmark. And this is sort of the first time we were able to train actually more than about, I think in the paper we had about 100 million parameter models, but we have been able to since then also train it up to like 500 million parameter models on this kind of data. And this is the first time, at least that I'm aware of an RL approach being able to do this. So that's the bit of excitement for me, because in some ways what this tells us is if we can figure out what exactly is the difference between RL and supervised learning, we can address that difference and get methods that can reliably scale up with model capacity and benefit in the same way as modern supervised and generative modeling methods are benefiting from. Okay, so I think I would basically stop at this point, but the key takeaways here are that large models can hurt naively instantiated in offline RL. And a simple way to address this is to sort of understand what might be going wrong. And we try to do this from the lens of implicit regularization. And turns out that by simply undoing some terms in this regularizer that do not appear for the case of supervised learning, we were able to get results that show that offline RL methods can scale well. They can use large capacity models. They can generalize pretty much in the same way as supervised learning methods, which just gives us more confidence that we can run RL on lots and lots of diverse data and hope to get good behavior out of it, much better than imitation learning and decision transformer style methods out there. Okay, yeah, so that was basically what I wanted to cover today. I guess I'm happy to take some questions now. Yeah.
First of all, let's thank the speaker. Yeah, and I think we have questions.
Yeah. Sorry, is there a question or?
Yeah, I'm asking. Do you have any questions? Please ask.
Yeah, and I'm sorry for going over things somewhat very fast. So I'm happy to also stick around and go over more details of some things if you want.
Yeah, it would be interesting to learn more about implicit regularization, but probably not right now yet, because we also limit in time. Okay, so I think we could chat like offline about some specific topics, but for now, thank you one more time.
Yeah,
it was really nice.
Yeah.
Thank you.
Thank you for calling me. Yeah, that's great.